This landscape of jagged peaks and deep craters is actually steel that has been left to the elements. 40 years of deep oxidation have created a thick, crusty shell where smooth metal used to be. The shackle is fused to the main body, seized by a grip of iron oxide. The original key was lost decades ago. To get inside, we have to reverse engineer a locking mechanism we can't see without shattering the fragile parts we are trying to save. Rust has migrated deep into the iron, compromising the metal's structural integrity and leaving it brittle. If we attempt to hammer the jammed screws or pry the shackle open, those internal components will likely snap. We have to rely on chemistry and thermal dynamics to gently break the tension and coax the metal apart. We start with penetrating oil. This fluid is designed with low surface tension, allowing it to seep into microscopic gaps and lubricate the fused threads of the screws. Targeted heat follows.
The flame causes the outer metal to expand, breaking the rust's grip while leaving the internal steel's hardness intact. With the casing open, we can finally reach the internals. We extract delicate springs and levers, all of them encased in a mixture of dirt and oxidation, and lay them out on the bench. This pile of rusted parts is a deconstructed map of the damage. We can finally see the work ahead of us. Cleaning begins mechanically. We use stiff wire brushes to scrub away the thickest, flakiest layers of exterior rust by hand. The pieces then go into a vinegar bath. The mild acetic acid reacts with the iron oxide, creating streams of bubbles as it dissolves the microscopic bonds of the rust. For the larger components, a sandblaster shoots fine abrasive particles at high speed. It strips away the remaining decay to reveal the bare iron underneath. The decay has been chemically and physically erased. We are left with a clean slate for the engineering challenge. The rust claimed a few casualties: one snapped internal spring and a lever heavily worn down by friction. We take a fresh piece of steel wire and bend it into shape, fabricating a replacement spring that matches the original tension. Now we face the primary obstacle: cutting a brand new key from a blank piece of brass by reading the lock's internal mechanism. Inside, 3 distinct levers of varying heights block a horizontal bar. As long as they are uneven, the shackle stays locked. To open the lock, a key must lift each lever to a uniform height simultaneously. Only then can the sliding bar pass through. We use a technique called impressioning. We coat a blank brass key in dark ink, insert it, and twist it hard against those internal levers. The ink is scratched off exactly where the levers made contact. We use a fine file to grind away metal only in those marked spots, repeating the process with microscopic precision. After hours of filing, we insert the key one last time. We apply pressure, and the mechanism finally clicks. That single mechanical click signals that the internal puzzle is solved. If you enjoy watching these machines return to life through engineering, subscribe to follow our next project. The internals are pressed against a high-speed polishing wheel, transforming the dull brass and steel into mirror-like surfaces. For the main casing, we are choosing to leave the heavy iron body unpainted. Instead, we apply a transparent clear coat to seal the sandblasted texture and create a barrier against future moisture. This clear coat preserves the pitted texture of the iron, turning the scars of 40 years into a permanent part of the design. Reassembly is smooth. We apply a thin coat of fresh grease, and the pristine parts drop into their slots. We insert our handcrafted key, give it an effortless turn, and the shackle releases with a heavy snap. Look at the comparison between the original rusted block and the restored machine. This piece of history has been given a second life. Thanks for watching.